Good morning. Thank you for being here. Today, I'm going to be discussing the acid catalysis properties of metal organic frameworks. Specifically, I'm going to be discussing MIL-100 catalyzed acetalization of benzaldehyde with methanol and the nature of active sites for this chemistry. So, what is MIL-100 and what does its structure look like? MIL-100 is a metal organic framework that is comprised of trimeric oxo-centered metal nodes. Um, so the nodes have a central oxygen which bridges three metal atoms. In our case, the metal atoms would be iron or chromium. These metal atoms are bridged by trimesate linkers, and the trimesate linkers connect these trimeric oxo nodes into an extended structure that results in two kinds of cavities, each of which are accessible through 6 angstrom and 9 angstrom windows. These nodes each carry two labile water ligands and one anion that is typically either a fluoride or a hydroxide. And we've shown in previous work that using thermal treatments between room temperature and 250 degrees Celsius, we can access all of the potential open metal sites in the case of iron and chromium MIL-100. These open metal sites and the metal oxo moieties that result from them can be used in low temperature alkane oxidation reactions and even in CC bond formation reactions like ethylene oligomerization. The reaction that I'll be focusing on for the purposes of this talk is a less industrially relevant reaction, but it's a probe reaction that helps us decipher the nature of active sites for this acid catalyzed chemistry. So we use acetalization of benzaldehyde with methanol as our probe reaction. And this is a reaction that can be run under relatively mild conditions. A significant part of the motivation behind choosing this reaction is that despite many studies reporting catalytic data on MIL-100 ion for the acetalization of benzaldehyde with methanol, the source of catalytic activity for this chemistry remains a major point of contention, with both Brønsted and Lewis acid catalysis being claimed in multiple reports. So the goal of our study is to identify the nature and density of active sites for the acetalization of benzaldehyde with methanol over MIL-100 ion. And for this purpose, we mainly use in situ titrations with different probe molecules and thermal treatment protocols described on the previous slide that we and others in the literature have developed for this material. So let's get started discussing the catalytic performance of MIL-100. Shown here are the moles of BDA per mole metal as a function of time in a batch reaction. The moles BDA per mole M represents the net turnover number, that is, it's the number of acetalization turnovers in the forward direction minus that in the reverse direction as a function of time. So I'll emphasize that BDA is the only product formed in this reaction, and the moles of BDA formed correspond closely to the number of moles of benzaldehyde reacted at any point in time. Another quick check before we go on to our titration data. In order to make sure that the catalysis does originate from the heterogeneous catalyst and not from leached species in solution, we carried out a filtration test where the filtration was carried out at 15 minutes. And noting that the residual activity after filtration corresponds closely to the activity that was measured without a catalyst, we at least have some level of confidence claiming that the acetalization activity originates from catalysis over the actual MIL-100 framework and not from lead species in solution. Now let's look at the titration data. Two separate molecules were used for our in situ titrations, 2,6-ditert-butylpyridine and pyridine. Note that 2,6-ditert-butylpyridine only titrates Brønsted acid sites selectively and does not titrate Lewis acid sites, whereas pyridine titrates both Lewis and Brønsted acid sites. When we plot the fractional reduction in net turnover number as a function of titrant to metal ratio, molar ratio, we find that pyridine is able to titrate all most all of the catalytic activity at a nitrogen to metal molar ratio of 1. On the other hand, DTBP leaves a significant fraction of the acetalization acetalization turnovers untitrated even at a nitrogen to metal molar ratio of 1. So one conclusion that we can reach even with this preliminary data set is that Brønsted acid catalysis does contribute significantly and maybe even contributes to the majority of the acetalization catalysis under these reaction conditions. The question is, why do we see this difference between the DTBP and pyridine titration data? There are two possibilities here. One is that the contribution of Lewis acid sites to acetalization is significant under these conditions. The second possibility is that DTBP simply cannot access all of the Brønsted acid sites under reaction conditions, unlike pyridine, which can. So to evaluate the former possibility, which is the contribution of Lewis acid sites, we use certain thermal pretreatment protocols that have been developed by our group and others. So the basic idea is that increasing activation temperature leads to increasing access to open metal Lewis acid sites. So at the lowest activation temperature, we expect almost no Lewis acid sites, but a lot of Brønsted acid sites originating from water ligated to the metal sites. Whereas at the highest activation temperatures, we expect almost every chromium atom to be acting as a Lewis acid site. So when we look at the net turnover number at 15 minutes, as a function of pretreatment temperature, we see that the net turnover number decreases monotonically with increase in pretreatment temperature. And crucially, at the highest pretreatment temperature, which is 250 degrees Celsius, we observe that most of the activity disappears. This experiment in and of itself, we believe, disproves the possible contributions or possible significant contributions of Lewis acid catalysis in acetalization at room temperature. And reinforcing this interpretation or conclusion is the fact that once the material activated at 250 degrees Celsius was rehydrated for a couple of hours, most of the catalytic activity of MIL-100 was recovered. So these data strongly suggest that it is the Brønsted acid sites and not Lewis acid sites that contribute that are responsible for acetalization under these conditions, and that maybe the water molecules ligated to the metal atoms are the source of this Brønsted acidity. So what we did next to probe this further was we looked at the infrared spectroscopy data. There are two separate hydroxyl peaks in the high wave number region. The peak that has a higher wave number here is associated with water molecules ligated to chromium, and the one at lower wave numbers is associated with hydroxyls bound to the chromium. There we go. So as expected, we see that the areas of both of these peaks decrease, the intensities of both these peaks decrease, but the question is, can water molecules that are bound to the chromium act as Brønsted acid sites? And to here for the infrared spectrum to load, yes. So what we observe is that the intensity, what we observe is that the wave number of the hydroxyls corresponding to the water bound to chromium sites shift monotonically to lower wave numbers, indicating that a smaller fraction of the water molecules have hydroxyls that are not bound to the nitrogen in DTBP. Moreover, as we decrease the treatment temperature, we do observe an increasing intensity of the peak corresponding to DTBP bound to Brønsted acid sites. We also emphasize that this same NH vibration has been detected and used extensively for characterizing Brønsted acid sites in zeolites. So we do see evidence of Brønsted acidity originating from originating from water ligated to the chromium atoms. And as we've already discussed, the area intensity of the water peak goes down monotonically, uh, and the and with increasing treatment temperature, and so does the peak corresponding to NH vibrations from DTBP. In fact, the area of the DTBP and H band uh, correlates linearly with the area that corresponds to the water chromium. Not only that, but also the catalytic performance can be related to the area of the water, area of the peak corresponding to water in the infrared spectra. What we see here is that at different times, 15, 30, and 60 minutes, the net turnover number decreases monotonically with increasing treatment temperature. Not only that, but at every single time point, we see that the net turnover number increases linearly with the area of the water peak. So this is indicating or providing evidence for the participation of these water molecules as Brønsted acid sites in acetalization at room temperature over MIL-100 ion. So what we've seen so far is that using a combination of in situ titrations with both DTBP and pyridine and thermal treatment protocols and infrared spectroscopy data that tracks the areas of these tracks the hydroxyl vibration corresponding to these ligated water molecules, we're able to suggest that the Brønsted acid sites originating from these water molecules are responsible for acetalization performance. But this still leaves open the question as to why we have a fraction of sites that cannot be titrated by DTBP, which is a selective titrant for Brønsted acid sites. And we earlier in the talk we discussed two possibilities. One was the possibility of a contribution from Lewis acid sites, and the other was relating to the limited accessibility of DTBP to a portion of the Brønsted acid sites in MIL-100. So, based on water adsorption isotherms measured in our lab and molecular modeling studies from other groups, we're able to estimate the fraction of chromium atoms that reside in the larger cavities versus smaller cavities. And what we find is that about 42% of the chromium atoms of the total chromium atom, reside inside the larger cavities, which can presumably be accessed by DTBP. Whereas the fraction of sites that can be titrated by DTBP, on the other hand, are 63%. So the disconnect between the 42% of sites that are in the larger cavities and the 63% of sites which can be titrated indicate that the size of the cavity may not be what differentiates the sites that can be titrated from those that cannot. But we still wanted to probe further and see if our explanation as to limited accessibility to some of the Brønsted acid sites is valid. And for this purpose, we synthesized three different materials that had the same chromium oxo-centered trimer node, but had different levels or different degrees of diffusional constraints surrounding the chromium oxo trimer. So on the top is MIL-100, which has the smallest pore window sizes. MIL-101 has larger window sizes for both cavities, and the homogeneous complex, which does not have a pore size associated with it, obviously, but can undergo some sort of agglomeration under reaction conditions. And we wanted to test the effect of pyridine and DTBP both on these three materials. So what we see is when we look at the fractional reduction in net turnover number as a function of DTBP to chromium ratio, is that these fractional reductions are independent of metal identity, but these fractional reductions increase systematically when we alleviate diffusion constraints around the oxo-centered trimer node, consistent with limited access of DTBP to Brønsted acid sites being responsible for the incomplete sequential titrations involving DTBP and pyridine reinforce these conclusions. What we're doing here is we're first dosing in DTBP and then introducing pyridine after we see no change in the spectra after a certain number of DTBP doses. And what we observe is that there is a shift in the OH frequency after injection of pyridine subsequent to the DTBP injection first and introduce a series of pyridine injections first, followed by DTBP injection. What we will note is that there is no further change in the frequency of the hydroxyl B. So what this is indicating is that because pyridine accesses every single Brønsted acid site, the introduction of DTBP after these pyridine pulses uh, does not result in any change in the OH frequency, unlike the converse experiment was described on the previous slide. So what I've shown using a set of materials that have different diffusional constraints and sequential titrations and some water versus methanol data that I don't have the time to go into is that Brønsted acid sites are predominantly responsible for MIL-100 catalyzed acetalization under the conditions of our experiments. And before I end, I want to thank my research group and specifically Jacqueline Hall, who's the student that did all of the work described here. And I also want to thank ACSPRF and various UH internal funding sources. Lastly, if you're interested in not only the acid catalyzed properties, but catalysis properties, but also the low temperature alkane oxidation properties of metal organic framework materials, I would encourage you to attend Jacqueline Hall's talk on Thursday morning in the microporous, mesoporous, and mesoporous materials metal chemistry session. And with that, I'd like to wrap up, and I'd be happy to take any questions virtually, of course.